Hey guys, welcome to Pre-Calc Lesson 12.12. Finally, we made it. More graphing rational functions. So we're going to kind of pick up where we left off in the last lesson. If you really have a good grasp of it from our last video lesson, this might be a little bit redundant, but if you're still struggling a little bit with this concept and want to see a few more examples, I'm just going to go through 4 more examples here, but don't feel like you have to watch every single one of them. So from yesterday, we talked about if I want to graph a rational expression, first thing I need to do is determine where it has discontinuity. And if you remember, that's setting the denominator equal to 0. So first thing I'm going to do here is figure out where I have discontinuity, and that's pretty easy to do. That's going to be when x is 0. Okay, because if I plug in a 0, guess what? Denominator is 0. So now what we do is we take the limit of the function as x approaches 0. Now, I know direct substitution is not going to work, so what I'm going to try and do next is I'm going to try and factor this expression. Well, I can't factor this. 6x squared minus 4 doesn't factor. I could take out a GCF of a 2, but that's not really going to do anything for me. So I have to use that expression. And when I plug in a 0, I'm going to end up with a 0 in the denominator. Okay, so this is going to end up being negative 4 over 0, which means that limit does not exist. So remember what we said. If we have discontinuity and the limit does not exist, that's going to indicate a vertical asymptote. Okay, so this tells me I have a vertical asymptote at x equals 0. Okay, so I like to sketch it in. As I find a piece of information about the rational function, I like to sketch that in. So here we go. And I'm going to have a vertical asymptote right there. Okay, so the next thing I do is find the limit as x approaches infinity of my expression. All right, well, remember, limits to infinity, basically we look for the variable with the greatest exponent. Well, it's squared in both the numerator and denominator, so my limit as x approaches infinity is going to be the ratio of those coefficients. All right, so that's going to be 6 over 3 or 2. So what this tells me is x approaches infinity, the y value is going to approach 2. So that gives me a horizontal asymptote at y equals 2. So again, let's put that in. Y equals 2, horizontal asymptote. Okay, so where do we go from here? Well, I like to find roots, all right? I know there's going to be roots because notice this is not an asymptote, so I'm guessing I'm going to have some value of x here and or here. So to find roots, if you remember, that's going to be numerator equal to 0. All right, so my numerator is going to be 6x squared minus 4 equals 0. 6x squared equals 4. X squared equals 4 over 6. So remember, careful here, x equals plus or minus 2 over radical 6. Now, this is really calculator inactive. I doubt you'd have one like this that you have to evaluate, but if I just kind of ballpark this, that's going to be plus or minus approximately 0.8. So remember, plus or minus, that's going to give me 2 roots, approximately here and approximately here. I'll tell you right now, I can graph this function. All right, I can make a good sketch at least, because remember, I've got an asymptote here, I've got an asymptote here, I've got a root here and a root there. So I know it's got to look something like this. That's the only thing it can do. So let's sketch that in. I know there can't be anything up here, and I know there can't be anything up there. So this one looks a little bit different than the ones that we did in the last lesson. I know there's no y-intercept again because this is an asymptote. Now, in terms of symmetry, if the question specifically asks, is it even, is it odd, or neither, I can take a look at this picture and see it has symmetry with respect to the y-axis. So I can tell you right now, this is an even function. Okay, if it just says to sketch, you don't have to offer that, but I think you might see down the road even, odd, or neither. In this case, that would be even. All right, our next example. first thing before you do any simplifying, I can't emphasize this enough, is you have to find discontinuity. Discontinuity is where this is going to be equal to 0. All right, so I might even just write that out. All right, so I'm going to have discontinuity at -5 and +5. So now, what do you do once you know where you have discontinuity? You find the limits there. So I'm going to take the limit as x approaches -5. And I'm going to take the limit as x approaches 5. Now, and only now that we've established where it has discontinuity, do we simplify the expression up above. All right, so let's factor this. Let's see, signs are the same, both negative. Okay, so that's going to be x minus 5, x minus 2. This we've already done, x plus 5, x minus 5. Now I can cancel those. And what I'm left with is x minus 2 over x plus 5. That is going to be my simplified expression that I'm going to use for the rest of the problem. Okay, so let's plug that in. X minus 2 over x plus 5. Now I can evaluate the limit. Let's put in a -5 here and here. I think you guys can see what's going to happen. I get like -7 over 0. That does not exist. So what have we said? I have discontinuity. The limit does not exist. That's a vertical asymptote at x equals -5. Again, you don't have to do it in this particular order. I'm a big fan of once I find something, I put it in the graph. So at -5, I have a vertical asymptote. Okay, well, let's find the limit now as x approaches 5. So I have x minus 2 over x plus 5. Plug in a 5. That's 5 minus 2 over 5 plus 5. 3 over 10. So what does that tell me? That tells me that my function has discontinuity, but the limit exists. So I have a hole in the function. Okay, so that's going to be a hole at x value of 5, y value of 3/10. So let's put that on our grid here. 5 and 3/10. So again, we're just kind of estimating this. I know it's not great, but it's obviously between 0 and 1. You have a hole in your function right there. Please make it clear that that is an open circle. The function does not exist there, all right, but the limit does. So I know I've got something, I don't know exactly yet, but something like that. Okay, so now what I'm going to do is I'm going to take my limit to infinity. Limit as x approaches infinity of my simplified expression. So I'm looking for greatest exponents. Both have a degree of 1, so it's going to be the ratio of these coefficients, 1 over 1. And limits to infinity mean we have a horizontal asymptote at y equals 1. Okay, so y equals 1. I know, I'm sorry if my grid here is really small. So I have a pretty good idea of what's happening. Asymptote here, asymptote here. I'm going to have something that looks like this. Now, this picture is going to be much more accurate because I believe there's going to be a root somewhere in here and a y-intercept somewhere in here. So I'm going to be able to get those two pieces of information. So let's do that. For roots, we're going to take the numerator and set it equal to 0, right, of my simplified expression. So it's going to be x minus 2 equals 0, so x equals 2. That's a root. Okay, let's put that in our graph. X equals 2. The y-intercept. How do we get the y-intercept? Well, if you remember, for y-intercept, we set x equal to 0, and whatever we have left is our y-intercept. So it's going to be 0 minus 2 over 0 plus 5, so that's -2/5. So -2/5 is between 0 and 1. It's going to be approximately right there. So now I have a pretty good idea of what this piece looks like, right? Asymptote there. It's got to go through these and approach that asymptote. Again, just please make sure it's clear that the hole in the function is an open circle. Don't go through that. That's an open circle. So at this point, it's obvious to me that this function is not even, it's not odd. It doesn't have symmetry with respect to the y-axis or the origin. So I only need to do one more thing. I need to figure out where that other piece is. I know it can't be here, because then it wouldn't be a function. So it's either going to be here, something like this, or it's going to be up there. So what I'm going to do is I'm going to pick the smallest number, and I'm just going to plug it into the function. I'm going to determine whether I'm up here or whether I'm down here. All right, so let's do that. F of negative 6. Again, you can plug this into the simplified expression. So I've got negative 6 minus 2 over negative 6 plus 5. It's going to be negative 8 over negative 1, which is positive 8. All right, so I know the point negative 6, 8 is on this graph. So it goes way up here. Again, we're just sketching, all right? So I just want you to indicate to me you understand that's an asymptote, that's an asymptote. So I'm gonna have something that kind of looks like this. All right, let's try a couple more. Example 3. All right, we've got f of x equals x squared minus 2x minus 15 over x minus 5. Again, please remember, first thing you do, denominator equal to 0. That's going to tell you where you have discontinuity. So pretty obvious here, it's going to be at 5. Only one place. So that means I only need to take one limit as x approaches 5. And let's simplify this while we're here. It looks like that's going to be x minus 5, x plus 3 over x minus 5. And these cancel. So my simplified expression is simply just x plus 3. Okay, plug that in. Now I can plug in a 5. 5 plus 3 is 8. So what do we know? We have discontinuity, but the limit exists. That's this situation. That's going to be a hole in the function. So that's called point discontinuity. Graphically, we're going to say we have a hole at 5, 8. So again, I like putting this on my graph. 5, 8, there's a hole in the function. So that's going to be an open circle at 5, 8. All right, well, there's no other discontinuity. So I know I'm not going to have a vertical asymptote or any other holes in the function. So that's it. Now I can move on to my limit to infinity. Well, that's simply going to be infinity, or the limit does not exist. So I know basically I have no horizontal asymptote. Or graphically, it'd be nice if you guys understood as x goes to infinity, y is also going to go to infinity. So graphically, I know I'm going to have something that looks like this. All right. And now what I need to do is get some other points. Can I get maybe a y-intercept? Can I get some roots? So I have an idea of where this graph is going to go. All right, so let's do roots. Roots would be numerator equal to 0. Well, the simplified expression is x plus 3, so that's x plus 3 over 1. So set that equal to 0. X plus 3 equals 0. X equals negative 3. All right, that's a root. X equals negative 3. There you go. And I think the last piece that I need is going to be my y-intercept. And remember, to get the y-intercept, you're just going to set x equal to 0. So y equals 0 plus 3, y equals 3. And that's it. So I think I have a pretty good idea of what's happening here. I know we're used to seeing hyperbola shapes, but this is simply going to be a linear function that has a hole in it right there, point discontinuity. Now, obviously, this does not have even symmetry or odd symmetry, so you don't need to go ahead any further with that. So I think at this point, I'm going to call it. I don't think you guys need to see another example or hear my voice anymore. So I will put the other one on Schoology just in case you want to see an extra one. But this concludes our unit on limits. Please reach out. I know this unit is probably the most challenging unit and the hardest one to do virtually of all the units we do this year. So please reach out with any questions. If you want to see additional examples, please contact Mr. Ward or myself, and we'd be happy to post some more material if needed. Okay, thanks for following along, guys.